Okay, hi everyone. It's my big pleasure to welcome you to this week's seminar and to introduce you to our today's speaker, Paola Todino. Paola is going to give a talk with mathematical background, and her timeline in academia until now is also very much on the mathematics side. She studied in Rome, and then she did her PhD in L'Aquila. And then she did several postdocs, one of them in Bochum in Germany. And now, actually, since yesterday, she's back in Rome in a new postdoc position in University La Sapienza. And she's going to talk about flexible bandwidth needlets. The floor is yours.
So good morning, everybody. And thank you very much, Mira, for the introduction and also for the invitation. I'm really happy to be here. Today I will talk about these flexible bandwidth needlets, which are a form of spherical wavelet transform. So first of all, I will introduce the standard needlet construction, and then I will show you how, with Claudio Durastanti and Domenico Marinucci, we generalize this kind of needlets to admit more flexibility in the harmonic domain. So, first of all, I want to say that for the analysis of spherical data, we can use two kinds of approach. The first one is through the harmonic analysis, which corresponds to the Fourier analysis in the circle in the Euclidean plane. And the second one is through this spherical wavelet system. Among the spherical wavelet system, there are these needlet systems, which have been introduced for the first time by Narkovich, Petrushev, and Warp in 2006. And then they have been applied to random fields and cosmological data by Baldi, Kekiakarian, Marinucci, and Picard. So there are a lot of literature for the needlets. So I mentioned just few papers of the last 5 years. But a lot of people work within needlets. So we can see, for example, Olenko, Pizzi, Wang, Durastanti, McEwen, and Wang, Leja, but these are just few authors. So we are interested in the application to random fields because they are important for application, most of all in cosmology, because the cosmic microwave background, for example, can be seen as a single realization of an isotropic random field on the sphere. But we can find also application in geophysics or astrophysics, climate sciences, so all contexts where data are collected on a sphere. So, okay, so usually when we deal with the cosmic microwave background models, for example, we prefer to use the harmonic analysis because we know the behavior at each, we can study the behavior at each single multiple separately. But sometimes for statistical applications or for implementation, it's not always easy to use this kind of approach because it is necessary to observe the random field on the entire sphere. And this doesn't happen in the real life because, for example, if we think to the sky, there are some masked regions which don't allow to observe the full process. And for these reasons, we prefer to use the needlet. So we have two main properties. The first one is that they represent a tight frame. So I know that for the moment everything seems too abstract, but I will give also the proper mathematical definition of this property. So, and also the construction of the needlet, of course. So just to know that the tight frame allows for a reconstruction formula. So we can rewrite our random field starting from these needlet systems. So using the needlet system, we can reconstruct the process. The second main property is the uncorrelation properties in the high resolution sense. So when the frequency goes to plus infinity, because the uncorrelation property, it's useful for the applications to random fields because if we are, for example, under the hypothesis of Gaussianity, uncorrelation means independent, and then it means that we have a sample of independent random variable. So you can do some statistics. And this property has been used in a lot of papers for applied to random fields. So the paper with Mira is just an example, but also Cammarotto and Marinucci in this paper of Burgendo Rassanti. It is essential to prove for testing non-Gaussianity, for the point source detection, which is a very interesting application for physicists in polarization analysis. And I mean, just few examples. So in these pictures, I wanted to underline the difference between the Fourier analysis approach and the needlets. So the concept is that when we use the analysis, the Fourier analysis, the harmonic analysis, we know what it happens at each multiples, but we lose information on the space because this is the Heisenberg principle. So we are not able to observe at the same time the space and the harmonic in the harmonic domain. So when we use the harmonic analysis, everything seems equal. So everything is smoothed equally. It is the dashed line. While needlets allow to enjoy a good localization property in space, but of course we lose something on the harmonic domain. So we, instead of considering each multiple, we consider a window of multiple, but we gain in space. We gain information in space. So needlets are very localized. So for example, we cannot recognize the peaks using the harmonic analysis, but we can recognize peaks of the process using the needlet because they emphasize locally what it happens. So here he emphasized this point here, and the rest is flattened. Okay, so now it's the moment for mathematical background. So let us consider the set of square integrable function in S2. This can be decomposed into the space of harmonic and homogeneous polynomial of degree L restricted to the sphere. So HL is this space. And the dimension of HL is 2L plus 1. So the function who belongs to HL are the eigenfunctions of the Laplace-Beltrami operator. So they are the eigenfunctions of eigenvalue minus L times L plus 1 of the spherical Laplacian. We can choose a basis of this space, and we call this basis YLM, the spherical harmonics, the so-called spherical harmonics. And then it means that if we take a function f in L2 of the sphere, we can write fx as a combination between some coefficients and the spherical harmonics, the basis. The coefficients ALM are called spherical harmonic coefficients, and they can be computed with the inverse transform of f. So for example, if we want to implement ALM, we need to know the random field f. I mean, I said random field, but until now, this f can be also deterministic, a deterministic function. By the way, we need to know fx on the entire sphere. So this cannot be done always because of what I was saying before. So we cannot observe always the entire process because of the masked region. And so, and needlets allow to escape this problem because thanks to the uncorrelation property. So the idea is this one. If you imagine that your sphere is divided in some pixels, so what it happens in one of them, it doesn't care about what it happens in another one. So the uncorrelation means something like that. So we are able to reconstruct the process without observe all the field. So now we introduce this kernel, ZL, like this kind of product between the two spherical harmonics. So x1 and x2 are 2 points of the sphere. And there is this addition formula which links the product of two spherical harmonics to the Legendre polynomial PL. So PL is the Legendre polynomial. And okay, this ZL, this kernel, enjoy also a reproducing kernel property in this sense. So the integral of the ZL evaluating in the standard, this is the standard scalar product in R3, okay, because we are seeing the sphere embedded in R3. So evaluating in the product between X and Z, here we have ZL prime evaluating in the product between Y and Z, and we obtain ZL evaluating in the XZ, like a triangular formula, let's say. So delta is the Kronecker delta. So for any function f in L2 of S2, the projection into the space HL is given by this integral, and we find this sum here. So if we come back, this is exactly this guy. This is the projection into the space HL. So Fx is the sum over L of all this Fl. So the standard needlet kernels introduced by Narkovich, Petrushev, and Vart is the following. So they considered the kernel ZL times a weight function B, which is evaluated in L divided B power to J. So L is the frequency. B, big B, is a parameter, so it's a fixed parameter. It's just a number bigger than 1. The weight function B is infinitely time differentiable. It has compact support in 1 over BB, and it represents a partition of the unity, so this property here. So the authors proved that this needlet kernel enjoy a good localization property in space. Namely, we can bound this function phi j by a constant which doesn't depend on j. Okay, you have to imagine that b power to j, it's like L. So when j goes to plus infinity, it means that the frequency is going to plus infinity. So Cm doesn't depend on j, and here we have p power to j and divided by this guy here. So when j goes to plus infinity, this guy goes to 0. So they are more and more localized when j goes to plus infinity. Here, this distance here is the geodesic distance on the sphere. So it is defined as the arc cosine of the standard scalar product in R3 between 2 points of the sphere. But if you imagine, so we have this sphere, and if we use the polar coordinates, so phi is the angle between 0 and 2 pi, and theta is the angle between 0 and pi, then you have 2 points in this sphere, so we can fix x in the North Pole, then the geodesic distance is just the angle theta. So y is here, the geodesic distance is just theta. So in this figure, which I took from the paper of Guillaux, Fay, and Cardoso, I wanted to give an intuition about this needlet, this localization property. So this is the original map of a cosmic microwave background. I know that it's not very clear, but there are some red regions, so the hottest region, blue region, which are the coldest, the minimum of the field, and green. So you can see that when you apply the needlets to this process, we can recognize better the hottest region, the cold region, and the green region. So they emphasize locally what it happens. And when j goes to plus infinity, so in this picture j is equal to 2, here 3, 4, and 5, everything becomes more and more localized. So the needlet projectors is defined in this way. So here, this guy, it's exactly the same as before, of phi j, big phi. But we centered ZL, the kernel, on the cubature points. So we have the sphere, and we take some cubature points of the sphere, So xi, j, k are cubature points, and lambda, j, k are the weights. So this is a sort of convolution between the kernel ZL centered in the cubature points times the function b, and we need to multiply by the square root of lambda. So if you want to implement with LPX, for example, your CJK are the center of the pixel, and you can take a weight like 1 over the number of pixels you are considering. So the corresponding needlet coefficients are defined as the product in L2 of S2 between the function f, your random field which you want to consider, and the needlet projectors phi jk. So you obtain this guy here. So f can be random or deterministic. And we can prove that beta jk represent a tight frame. Namely, so tight frame means that the norm is preserved. So the sum over j and the sum over k of the square of beta jk, it's equal to the norm of f. And they allow also for a reconstruction formula, namely we can reconstruct fx taking this sum here of the needlet coefficients times the needlet projectors. Now we want to see the application to spherical random field. So we consider f an isotropic with zero mean and finite variance random field on the sphere. So isotropic means that the distribution law doesn't change under rotation. So the process fx has the same distribution law of the process fgx. So fx can be written in this way, as we have seen before. And now ALM are random because we are considering fx random. They are uncorrelated, and the variance is equal to CL. This sequence CL is called angular power spectrum. And in the paper of Baldicher, Kekarian, Marinucci, and Picard, and also in many other papers, they assume that the angular power spectrum satisfies this condition. So it's given by a function GL times L power 2 minus alpha, where the R derivative of G is a big O of U power 2 minus R. So now we define this new random field called needlet random field, beta Jx, in this way. So this random field, beta Jx, can be viewed as a continuous version of beta Jk. Indeed, if beta Jk can be found by beta J, evaluating beta J on the cubature point, Cjk, multiplying by the weight. So beta Jx is a random field. Beta Jk are some number, some coefficients. So Baldicher, Kekarian, and Marinucci, and Picard prove under the previous assumption on the angular power spectrum that these beta Jx, these random fields, are uncorrelated. Namely, that we can bound the correlation between beta Jx and beta Jy by a constant, which doesn't depend on J, divided by this guy here. So we have, this is always the geodesic distance between the 2 points x and y, and here we have b power 2j. So again, when j goes to plus infinity, this guy goes to 0. So the needlet random fields are uncorrelated. Okay, so these were the standard needlet construction. Now I show you the flexible bandwidth needlets. So with Claudio Durassanti and Domenico Marinucci, we wanted to generalize these needlets to admit more flexibility in the harmonic domain, because we think that this is important for application, because sometimes physicists, when we deal with standard needlets, the range of the multiples L is in between b power to j minus 1 and b power to j plus 1. But sometimes, I mean, maybe there are some physical constraints which doesn't allow to observe exactly this range. Maybe we miss some information, or maybe we should drop some multiples which we can observe that are available. In fact, for example, in the analysis of the cosmic microwave background, it happened that physicists changed the window function B of the multiples, but without a background theory would justify this choice. So we try to generalize the weight function B. So we considered the needlet projectors defined in this way, so exactly as before, but now we have this weight function BJL, which is more general. So to define BJ, I need to introduce the scale sequence Sj, starting with S0 equal to 1. So we assume that Sj is an increasing positive value sequence. It has a BJ as a compact support, as a support included in this range, so Sj minus 1 and Sj plus 1. The support of Bj and Bj prime are disjoint whenever J minus J prime is bigger than 2. This is a standard condition that holds also for the standard needlets. And we assume also this condition, so Sj minus 1 is increasing, but this is not important. It's just to have the statement more clear, because we already have the statement in terms of the maximum between two things. So if we don't have this condition, we will have the maximum between the maximum of other two things, but okay, it's just to make more clear the statement. So Bj depends on the sequence Sj, and is such that the n derivative of Bj can be bounded by a constant, which doesn't depend on J, divided by Sj minus 1 power to n. So in the end, I will show you that we can construct numerically this kind of B. So it can be done. It's not, so it exists a B which does this work. And so Bj is a compact support, as I told before, and it is 0 in the extremal points of this interval, and in Sj is equal to 1. And finally, it represents a partition of the unity, so it satisfies this condition. This property here, it's important for the reconstruction formula, for the tight frame property. There are also some needlets which don't have this property, but I think this is one of the important property of this kind of standard needlet, this kind of needlet. So, for example, if we are in the standard case, so if Sj is exactly the sequence b power to j, we can see that the standard needlet construction of Petrushev, Bard, Narkovich satisfy our assumption. So if Sj is b power to j, when we take the n derivative of bj, we have to do the n derivative of this guy here. So we have the n derivative of b, 2 divided by b power to j, and when we derive also respect to u, we obtain 1 over b power to j in front of these things here. So when we iterate the process, we have 1 over b power to n minus j, and this guy can be bounded by this one. So we obtain exactly our property. So we prove that the localization property holds also for this needlet. So when j goes to plus infinity, we can bound this needlet construction phi j by a constant which doesn't depend on j. Okay, and this guy here, so we have Sj plus 1 power to 2 minus Sj minus 1 power to 2, and then the maximum between these two guys here. So it's, I mean, quite similar to the property that Narkovich, Petrushev, and Bard found for the standard needlet. Indeed, If we consider the standard case, so if we substitute in our formula Sj with b power to j, we write b power to j instead of Sj, we find the maximum between these two guys, and doing small computations, we can find again the property, exactly the guy that they found for the standard needlet. So the flexible bandwidth needlet for small phi jk is defined exactly as before in the same way. So xi jk and lambda jk represent the set of cubature points and weights, such that the integral between the integral of the product of two spherical harmonics is also equal to if we take the sum over the spherical harmonics evaluated in the cubature points times the weight. So we have this property. And now we want to apply the localization property to the random field. So exactly as before, as we did for the standard needlet construction, we consider F an isotropic centered Gaussian field with finite variance. Sorry, I said Gaussian, but it's not necessary here. So F is exactly as before, can be written in this way. The ALM are uncorrelated, and the variance is equal to CL, which is the angular power spectrum. Now we consider this assumption on the angular power spectrum, which are a bit lighter respect to the previous one, because now CL is equal to GL times L power 2 minus alpha, but the function GL satisfies this condition. So, okay, it is bounded below and above by two constants, and the R derivative of G, it's a big O of U power to minus 1 minus beta times R. So in the standard needlets, the authors considered, assumed that G, the R derivative of G was U power to minus R. So it seems a small difference, but indeed is not, because this implies that we can take, we can consider a class of angular power spectrum a bit more general. I mean, so for example, our case covers this kind of angular power spectrum. So something which oscillates more. And this is important for the application because the angular power spectrum can oscillate. So we consider now the continuous version of the needlet coefficients, so beta jx, and we prove the uncorrelation property. So under this new assumption on the angular power spectrum, we can prove that there exists a constant Cm, which doesn't depend on J, such that the correlation, we can bound the correlation between beta Jx and beta Jy by this constant and the maximum between these two guys here. And now in the proof, of course, we use the localization property. So this is why the uncorrelation property is a consequence of localization property of the needlet. So now we prove that the flexible needlets form a tight frame and they allow for a reconstruction formula. So if we want to prove that the sum over J and the sum over K of the square of beta Jk is equal to the norm of F in L2, where F is the random field which we are considering. So we substituted the definition of beta Jk and we obtain this guy here. Sorry, it's missing a sum over M. I forgot a sum over M here. Then we open this square here and we obtain 2bj, 2ALM, and 2 spherical harmonics. Now we remember that this guy here is equal to the integral of the product of the 2 spherical harmonics. And it is known that the integral over the sphere of the product of 2 spherical harmonic is the Kronecker delta in L1, L2, and M1, M2. So it's not 0 only when L1 is equal to L2 and M1 is equal to M2. So here, the only thing that remains is sum over L, so 1L only because of this symbol here. And so we have the square of beta j and the square of ALM. Now we use the fact that the sum over j of bj squared is equal to 1, and we have exactly this guy here. And this is equal to the norm of f for Parseval's identity, because we are in orthogonal spaces. So Parseval identity holds, and we have this guy. And in the same way, we can prove the reconstruction formula. So we substitute the definition of beta jk, the definition of phi jk, and we can do exactly the same to obtain the reconstruction formula. Now, some remarks. So our uncorrelation property, in the case of the standard needlet, become this one. So if we substitute Sj with b power 2j, we obtain the right-hand side in the uncorrelation property becomes this one, which can be bounded by this guy. So when beta is equal to 0, here we obtain exactly the bound that Baldi, Kariyama, Rinucci, and Picard found for the standard needlet. So here we generalize the result to all beta in 0, 1. Okay, and now we can, with this flexible needlet, we can do all the applications that are already done also with the standard needlet. So these are some examples, so subsampling technique with total estimation. So the needlet can be used for testing for isotropy. The idea is that I mean, this is the real poor idea. So the intuition is that if your needlet coefficients, it's so evaluated in the North Pole, for example, it's a very huge number, and in the South Pole, it's a very small number, then maybe you don't have an isotropic field. And they have been used for point source detection. So in this paper of Cheng, Cammarota, Fantaillet, Marinucci, and Schwarzman, they considered signal plus noise. So they want to detect some point source. I mean, they want to understand if some peaks, so they have a signals, and they want to understand if the peaks are caused by some star, for example, some celestial body, or if it's just fluctuation of the cosmic microwave background. So they simulated a signal plus noise here. This is a simulation. And so the signal is the star and the noise is the cosmic microwave background. Then so here we cannot distinguish very well the peaks, but so they apply the needlet. So they, like a filter, they filter the process with with the needlet, and then they recognize the peaks. Once you have the peaks, they show how to construct a multiple test on these peaks to decide if to accept the hypothesis or not. I mean, this is just to give you an idea of the applications. So now we can see an example of how to construct a goodness of fit testing for the angular power spectrum CL. So we consider F a Gaussian isotropic random field and observed on a region D in the sphere. And out of this region, we want to check the goodness of fit for a given angular power spectrum CL. So what we can do is the following. We take the cubature point, CJK, so we denote, I really don't know the pronunciation of this letter, so I will call it E, okay? EJ denotes the grid of these cubature points. And we consider the following testing procedure. So we construct the needlets in this way, such that Sj minus Sj minus 1 is bigger than Sj minus 1 power to 1 minus beta. So we ask that Sj minus Sj minus 1 divided by Sj minus 1 can shrink to 0, but divided by Sj minus 1 power to 1 minus alpha, they cannot go to 0. And we compute the needlet coefficients beta jk. Now we choose a subset of the j of these coefficients, where the distance between the cubature points is bigger than delta divided by this guy for delta and epsilon bigger than 0. And we send the cardinality of our subset dj goes to plus infinity when j goes to plus infinity. So I think that this can be helpful to understand the situation. So we have the elements of dj, which are a subsampling of the cubature points of your grid, and there are some constraints on their distance on the cubature points which belongs on dj. So now we have the uncorrelation property of beta jk. So we can prove that the correlation between beta jk and beta jk prime can be bounded by this guy, and then we use the constraint that we have for the cubature points here. So we obtain this bound. So the point is that this correlation goes to 0. So we want that this correlation goes to 0 when j goes to plus infinity for k and k prime in dj. So now we consider these statistics. And this statistics is linked to the angular power spectrum CL. So if we know the behavior of these statistics, we have a goodness of fit test available for CL, for example, because we can compare the results with the theory. So we proved the expectation of ij. So now we study the statistics here. The expectation of ij is equal to 0. This can be seen easily here. And we proved that when j goes to plus infinity, the variance of ij is equal to 1. So indeed, the variance, it's the sum of all the variances here, and then we have to take also the sum of all covariances. So this guy can be checked to be equal to 1. What about this guy, which we call aj? We proved that aj goes to 0. So this is a very technical result, so maybe you can trust me. There is this Weeks formula that links so if you have a jointly Gaussian vector, so the expectation of all the components is equal to 0, the expectation of all the product here between the component is equal to the sum over some configuration, okay? But the important thing is that here you have the expectation of two components, so taken 2 by 2. And so this leads to, this allows to write the covariance function in terms of the correlation. And now the idea is that the correlation goes to 0. We know that the correlation goes to 0, so we prove that these covariances go to 0 when j goes to plus infinity. So we obtain this bound now with all the conditions that we assumed this guy goes to 0. Now we know that the variance of ij tends to be 1, so there are some results on Magliavin calculus, Stay-Magliavin calculus, which say that, I mean, if the fourth cumulant goes to 0, then the limiting distribution is Gaussian. And so we compute the fourth cumulant of our statistics. In the case of a zero mean random variable, the fourth cumulant is simply the fourth moment minus 3 times the square of the variance. So we compute the fourth cumulant and we use again the Weeks formula. Okay, so we write the fourth cumulant in terms of all the correlation. So the point is that this guy in the end is a Bico of 1 over the cardinality of dj. But we take the cardinality going to plus infinity, so the fourth cumulant goes to 0, and thanks to this result, we know that the limiting distribution of ij is Gaussian. And then, at this point, we have a goodness of fit test available. So I want to say something. For the uncorrelation property, we we didn't assume the Gaussianity. We don't need the assumption of Gaussianity of the random field. But in this example, we need the hypothesis of Gaussian. So here, at the beginning, we assume that F is Gaussian. And without this hypothesis, things become much worse. Okay, so now I want to show you how we can construct a weight function B, which do this work. So for the flexible needlet. So we can consider this kind of construction. So we take AJ, infinitely time differentiable function, which is 1 between 0 and Sj minus 1. And it is between 0 and 1 in this interval. So between Sj minus 1 and Sj. And then it is 0. So the support of Ju is in between, it's 0 Sj. And now we can take the window function Bj as the square root of Aj plus 1 minus Aj. So the first problem is that Bj, we wanted that Bj is infinitely time differentiable, but so the point is that when we take the derivative, we have this square root at the denominator. So we need to check when this guy is equal to 0, but the only problematic points are Sj minus 1 and Sj plus 1. And using the Taylor expansion in that point, it is easy to check that Bj is infinitely time differentiable. Now, a numerical recipe for Bj can be the following. So we start considering the function phi, which is also called bump function, a sort of bump function. So this is the exponential map evaluated in, the exponential function evaluated in -1/1 minus t squared, when t is in between -1 and 0 otherwise. So now we take the integral of small phi and we normalize in order to still have everything -1, 1. So this is just a number, a normalization number. Then AJU can be constructed starting from this exponential function. So AJU, it's 1 when u is in between 0 and Sj minus 1, is 0 when we are over Sj, and in between it is phi evaluated in this point here. So it's a composition between phi and a linear transformation tau Ju, where tau Ju is exactly this argument here. So we can compute explicitly the R derivative of this function. So we have to take the derivative of the composition. So we have the R derivative of phi evaluated in tau Ju times the R derivative of tau Ju. And it's easy to compute the derivative of tau Ju here. So we obtain just this guy. And this phi was the integral of small phi, the exponential function. So we obtain this r minus 1, so the derivative of order r minus 1 of small phi, the exponential function. And the derivative of the exponential function can be computed explicitly. So we can bound everything explicitly, and we find that the n derivative of Ju is bounded by this guy. So here we don't have any dependence on j at the numerator, and we have Sj minus 1 at the denominator, power 2n. So now our Bj, our window function, is the square root of this difference, Aj plus 1 u minus Aju, and again using so the derivative of decomposition, we use Fadi-Bruno's formula, so the derivative for higher order. The derivative of the I don't know how to say, sorry, of composition of function in higher order derivatives. So Fadi-Bruno's formula allows to compute also the n derivatives of Bju. So exploiting this result for Aju we can also prove this relation here. So this construction of Bj satisfy our assumption. And that's what I wanted to say. So these are some references which I mentioned during the talk. And thank you very much for your attention.